Dos, tres, cuatro.
Hi everyone, today we're going to look at properties of logarithms, section 5.3. Just as a recap to get us started, if you turn to the page that says logs fast facts, I want to warm up with this. And so to build upon our understanding of how to be able to calculate a basic log without a calculator, I want us to be able to try these questions here. So if you scroll down, you're going to see that there are 30 log questions, and each of these are solvable. It kind of reminds me of doing those like fast minute activities in elementary school or things like that. So what I want you to do right now is I want you to pause the video and I want you to try these 30 questions right now and see if you're able to answer them efficiently. So pause the video and give this a go. Okay, here's the big reveal. Let's take a look and let's see how we did on our logs fast facts. So I'll scroll down carefully, but right now I'll give you a chance to be able to look at this first half right here and see how you fared. And then if we scroll down to the second half, here's our answers for the second half right there. Okay, so hopefully most of those you're able to answer pretty quickly, and definitely ask some questions in class if any of those are things that you weren't sure about. Okay, so today we're going to take a look at a bunch of the properties of logs and what we call our log laws. If you turn to the very back page of your package, you'll see that there's a bunch of them summarized there. And so the way I go about this is I think I want to tell you what the law is. It's going to be in these big blue boxes here, and just know that that's what you have access to. And then after that, I'll try to work on trying to show how it works through some numerical examples. So our first example is something called the power rule. And the power rule, sometimes you'll hear me say it's the soccer kick, and I don't really know why I call it the soccer kick, because I don't really think it looks too much like a soccer kick. So the exponent, and when you have something log base a of x to the power of n, so it's being raised to the power of n, that n is able to kick in front. And so you could say that would be n log base a of x. And that's what you would have for your power rule right there. Now there's some restrictions to it, and we haven't talked much about restrictions because I know the way we've structured this, we haven't done the graphing component yet. What I want to say is this. If you think back to any of the examples that we had in our fast facts, our base in every single case was only defined when we had bases that were positive values. Look at our bases there, and they're all positive values. They could be rational, irrational numbers, but they're all positive numbers. And so the way logarithms are defined is you're taking a positive base. And so this a value is defined when a is greater than 0 and a doesn't equal 1. And the reason we say a doesn't equal 1 is because if your base was 1, then you wouldn't have something that would make something that would be an exponential shape. It would be something that would be flat, because you would have a base of 1 and then nothing would alter from it. So using a positive value for your base that isn't 1, you're going to always produce something that's going to have an argument, this x value right here, that's also going to be positive. And if you go back to your examples on these fast facts right here, notice again, look at each of these arguments. No matter what, you always produce something that was a positive value. There's no negative values right there. And that's because when you take a positive base and you raise it to a power of anything, it's going to result in a positive solution. I'll give one example right here. If we look at something like number 23, if you were to take that log and write it in exponential form, you'd be saying 2 to the power of negative 4 equals 1 over 16. And as long as this base is a positive value, then there's no way that I could ever create something that would produce something that would be less than 0. This has to be greater than 0, because whether my exponent is positive or negative, it always will create something that would be a positive outcome. So when you have a negative exponent like we do here, we know that that still creates something that would be 1 over 2 to the positive 4. Okay, so that addresses some of our restrictions questions as well. And so let's think about like what's happening here. Essentially what we're doing is we're taking the exponent and we're kicking it in front. If you know that log base 3 of 3 is equal to 1, another way of being able to say this would be something like this. Log base 3 of 3 is raised to the power of 1, and if this 1 kicks in front, I know that log base 3 of 3 just gave me 1, and so I have the number 1 there. Nothing too exciting. But if you start looking at a couple other examples, log base 3 of 9, what if I rewrote this and I said log base 3 of 3 squared? Well, I know that this 2, based off of what we're saying here, if you kick it in front, we'd have 2 log base 3 of 3. And I know that reduces to 1, and so I get the answer of 2. Right here we have log base 3 of 3 cubed, or 3 kicks in front, and we would have just an answer of 3. And if I had log base 3 of 3 to the power of 4, the 4 kicks in front, and I get 4 log base 3 of 3. So if I have something raised to the power of n, it makes sense that I could say that becomes n log base 3 of 3. The log base 3 of 3 reduces, and I'm just left with the power of n. Okay, so how can we use that for some of our questions? So the heart of logs actually starts, I think, right with these examples here. And I find this stuff so interesting. As you heard me say in our first log lesson, one of the main purposes that we use logs is to be able to solve for x when x is a variable. When x is an exponent. Of course, x is a variable. If you take a look at 7 to the power of x equals 350, we right now don't have the algebraic understanding to be able to solve for x. We could probably estimate a good answer. We could put in our graphing calculator and find an intersect point, but we haven't algebraically figured out how to be able to solve for x, but we can now by using logs. So I'm going to show you how to do this first example 2 different ways. The first way is this. Fresh from our rules is this idea of using the power rule. And so what we could do is we could say something like this. Whatever you do to one side, you do to the other side in algebra. And so we're going to do this. In the same way that you could square both sides, square root both sides, times both sides by 2, we could log both sides. And if you do something like that, then using your power rule, you could take a look at this x right here, and you can kick that in front. And if you do that, you would get x log 7 equals log 350. And then based off of that, you could divide by log 7 and divide by log 7. Now, we're allowed to divide by log 7 because that's just representing some sort of decimal number. We don't know what it is, but it's saying x is being times by log 7. And so if they're being times by each other, you could divide by log 7. You could never divide just by a log. It always has to be associated with a number. And that's because you could never divide by a square root. You could divide by a square root if there's a value underneath the square root. But log 7 is the number that we're dividing both sides by. And then you're left with something here that's going to say log 350 over log 7. And we're going to check in a minute on how to be able to put that into a calculator. But just hold on to that answer right now. Now, that's one very good way to be able to solve for this, and that's by logging both sides. But let's look at a second way you could also do this. 7 to the power of x equals 350 is in what we would call exponential form. Could you rewrite 7 to the power of x equals 350 in log form? So if you wanted to write this in log form, you would have log, and then your base is 7, so log base 7 of 350 would equal x. And this way is probably way better. And I would recommend doing something like this if you have a question as simple as this, though both ways are correct. But what it also means is that if x is equal to log 350 over log 7, and if x is equal to log base 7 of 350, then that must mean something really strange here. That must mean that log 350 over log 7 is equal to log base 7 of 350. And so these are equal to each other, and it's going to be something called the, let's write this in, the change of base rule, and we'll formalize that in a second. And what it means is when you have log base 7 of 350 on this right side here, you're allowed to rewrite that by saying log 350, whatever your argument is, divided by log of the base. So let's actually scroll down here, and we have this written here as our change of base rule. And if you have something in the form of log base b of a, we just need to understand that is equivalent to saying log a over log b. These are equal to each other. Okay, so that's the change of base rule. And then going back up here, we still haven't actually solved for this. We've solved for it in exact form, but let's see what we can do to be able to find out our answer using our calculator. We could round our answer to 2 decimal places or something like that. It didn't specify in this case. Can you, before we actually do this, could we estimate what we think the answer might be? It's saying 7 to the power of something equals 350. And if I'm thinking about my powers of 7, I know 7 to the power of 1 is 7, 7 to the power of 2 is 49, 7 to the power of 3 is, I think 343. I should actually double check that. And if it is, then we know that if 7 to the power of 3 is 343, then I bet that in this case, x is going to be 3.0 something. It's going to be just above the number 3, because 7 to the power of 3.01001, something like that, will probably give us the number 350. So that's an interesting way of being able to estimate this. But right now, let's take out your graphing calculators and let's see what we could do to be able to figure this out. Now, most of you, let's see what we got here. Okay, most of you have a TI-84, and if that's the case, then you have a couple ways to do this. So the best way is to press math, go up to log base, click on the log base, and lo and behold, you can type in all the logs that you want. So if we want log base 7, go to the right of 350, it is going to give us 3.01. Hey, that was a pretty good estimate that we had there. Maybe I've done this question before. But that is a great way of being able to solve for it using your calculator. Now, what you could also do is this. We said that there's 2 ways to express this. We could have also said something like log 350, close brackets, divided by log 7. And if this is true, like we've said, through our change of base rule, then we should get the exact same thing, and we did. So those are equivalent to each other, and if you don't have a TI-84, say you have an older graphing calculator, you might need to do the second way, but otherwise, hopefully you have your log base function for your calculator. If you have a Casio, then I would ask Jessica Young, and she may be able to help you out there, because I'm not sure how those work quite as well as I do with the TI-84s. Okay, so let's continue on here, and let's see what we could say from this. So we get an answer of something like approximately 3.01. Based off of this, can you solve for part B by any method? And if you feel good, why don't you move forward and see if you can work on part C and part D? So for part B, again, the method you use doesn't really matter. In fact, I encourage you to be an expert at both of them. I think because changing it to log form is a little bit faster, we should do that. We could say something like log base 6 of 9 is equal to x. It should be something a little bit more than 1. And so if you put that into your calculator, you get to 2 decimal places 1.23. For part C, again, you could do this either method. So if you want, you could say, well, log base 3 of 20 is going to be equal to 2x minus 1. So again, that's just going from exponential form to log form. And then from here, you could add 1 and then divide by 2. Now make sure that when you put this into your calculator, you have that bracketed off right there, so we know that it's just it's not log base 3 of 21 or something like that. So calculate that, see what you come up with, and you should get something like 1.86. Again, if you chose to do it the other way, as long as you come up with a 1.86, then that should be just as good. So just to try the first method, I'll do that for this question here. Let's log both sides. Log 100 equals log 4 to the power of 3 minus x. So based off of that, we can kick the 3 minus x in front. And that whole 3 minus x belongs to log 4, so I'm going to put that in brackets there. And then we could divide both sides by log 4. Some of you are saying, hey, could we not write log 100, but could we just write the number 2? And you absolutely could. Doesn't really help us in our calculation, but you could do that. And so then you're left with something in which you have this. I could leave it like this, log 100 over log 4. I could put it in my change of base form if I wanted to, but I want to isolate for x. And so I'm going to add x onto the left side, and then I'm going to subtract log 100 over log 4, knowing that you may have it written as this as well. And let's put that in the calculator, and let's see what we get to 2 decimal places. And you should get something like x equals negative 0.32. So again, multiple ways to be able to do these questions, but hopefully you feel a little more comfortable with being able to solve for x now when x is a variable. So we've identified our change of base rule, and then just to make sure that we're all good with the calculator, this part here I actually probably don't even need to have in the notes. It says use the power rule to solve for x in terms of log a and log b. They're just saying, could you rewrite this as saying log a over log b equals x? And then there's really not too much more to be able to do there. So I'll edit that out for next year. For example 2 here, it says round to 3 decimal places. So this is just saying, can I put these into the calculator? So just really quickly, let's make sure that everything's working really well. And we would get, for our first one here, to 3 decimal places, 4.170. Okay, log of the second one here is going to give us 0.783. And then the third one is going to give us 3.503. Okay, here's our next rule. We have the product law. Okay, so the product law is going to say this. Again, let's just say it as it is. Log base a of xy is equal to log base a of x plus log base a of y. So when you have a log in which your values are being multiplied by each other, you can separate them into two separate logs being added together. That's the rule. And here's some of the reason behind it. So we know that log base 3 of 3 is equal to 1. But what if we had something like this? Log base 3 of 3 times 3. Well, by definition, I could, using our product law, I could say that would be log base 3 of 3 plus log base 3 of 3. And that would be like saying 1 plus 1, which would give us 2. And we know that log base 3 of 9 is 2. This is just another way of being able to express this. We could do the same for these next few questions here as well. 3 times 3 times 3. And that would be like saying log base 3 of 3 plus log base 3 of 3 plus log base 3 of 3. And that'd be like saying 1 plus 1 plus 1. If you wanted to, you could have split the 27 and you could have said, wouldn't it just be log base 3 of 9 times 3? And you could do that. If you have this example here, you could say 3 times 3 times 3 times 3. And I think you get the point. So if you have log base 3 of 3x, if you have log base 3 of 3x, then you could have something like this. You could say log base 3 of 3 times x. And then that means that you could rewrite this and you could expand it and you could say something like log base 3 of 3 plus, log base 3 of x. And then that could be simplified and you can actually say it'd be 1 plus log base 3 of x. Okay, so we get the idea for how the product law works. Take a look at these examples here. Simplify as a single log. So right now, you're going to go backwards. You have the expanded form of the product law. And if you have log 4 plus log 6, and they share the same base, which they do, and they have to, in order to be able to join these, then we could rewrite that and go backwards and say that would be the same as saying log 4 times 6. Think about what would happen if you expanded it. You would go back to here. And then that could be simplified to say you have log 24, and that would be your best answer. In fact, I kind of boxed it as if it looks like a log. I don't know. That was a bit of a stretch. Okay. Okay, part B. If we wanted to expand this, what's being squared right now? The squared applies to what's inside the bracket. So let's deal with that first. And let's rewrite this as log. The square root of a squared is a, and b cubed squared would be b to the 6. So we're using some of our exponent rules. And then based off of this, if that's a single log, could we rewrite that as two separate logs? And we sure could. You could say that would be log a plus log b to the 6. I would say that would be a very good solution, but usually what happens is when you have something expanded, then you can take the exponent and let's soccer kick it in front, and that would be your most simplified form of being able to express this. So if we said something like that, then that would be great. Okay, let's do a log. Okay, I'll stop it after this. I don't know what I'm thinking. Okay. Okay. The quotient law. So once we learn the quotient law and we learn the product law, then we'll be able to put some questions together that can get a little bit more complicated. And I bet you could predict what the quotient law is just based off of what we've been doing. So right here, we could say this could be log base a of x subtract log base a of y. And if you want to see an example of that, well, what would happen if we had a question like this? We know this would be log base 2 of 16 subtract log base 2 of 2. And we know that that's equal to saying 4 subtract 1, which would be 3. And yes, that's true, that's 3. But imagine, look at this. What if I'd taken the 16 and the 2 and I just wrote it was an 8? I know that log base 2 of 8 is 3. So definitely everything that we did there to be able to subtract those logs must be true. Okay, so then how about for this next one here? We could say log base 2 of 8 subtract log base 2 of 2. And that's like saying 3 subtract 1, which would give us 2. And yes, that's 2, because log base 2 of 4 does equal 2. So that means, therefore, we can say log base 2 of x subtract log base 2 of 2 could be simplified to say log base 2 of x subtract 1. You can't really do much more than that, but you are able to expand it to that point. Okay, so now we have all these tools, and it's a little bit dry. We've gone through a bunch of rules. Now it gets into some questions in which we can ask some questions that can begin to really challenge us. And Michelson happens to be able to find ways to really challenge us. Okay, so the first question is saying simplifies a single log. We've seen a question like that with the product law. This would be saying log 12 over 4. And then that could be simplified to just saying log 3. For part B, I don't know if I would call this a shortcut or what to be able to say about it, but basically, if you were to join these first two right here, you would get log xy, and it'd be subtracted by log z. And now if you had something like that, well, you could say, couldn't that become something like log xy over z? And I actually don't need to do that first step. So this is correct. But what you can start to do is you can join the product law and the quotient law into just one operation. And the way that I would say this is every time you have something that's positive, then it's going to be on the numerator. If they're being added, it's on the numerator. If it's being subtracted, then it's being divided and would be on the denominator. So you could say something like log xy, because x is positive, y is being added, and z is being divided. Let's see how that could help us for some of these other ones. Let's actually do D next based off of that rule. So if you say something like this, yes, I could do all of these individually, or I could just say this is going to be log Tm over AQ. And that's because log A is being subtracted and log Q is being subtracted. So for part C here, I could do something like this. I could say log PQ subtract log Tm, and then that's going to become log PQ over Tm. Some of you may have said, well, are you allowed to expand this? And you are. And then you would be subtracting a log T and subtracting a log M. So of course the T and the M are going to be on the denominator. Okay, example 3. Write each log in terms of log 3 and log 5. So you're given log 45, and 45 is a purposeful number because if you think about 45, I would say that's the same as saying 5 times 9. And 5 and 9 are related to the log 3 and the log 5 that we see there, because that would be the same as saying log 5 times 3 squared. And then that would be the same as saying log 5 plus log 3 squared. And then in my most simplified form, I should kick this 2 in front, and I could say log 5 plus 2 log 3. For part B here, you could say something like this. You could say log 25 over 3. Well, you could say something like this. What if we said 5 squared over 3? Which could be something like log 5 squared subtract log 3. And this 2 could kick in front, and you get 2 log 5 subtract log 3. So hopefully that seems reasonable. And there's just so many different types of log questions you can ask. So you're saying, like, how many log examples do we have here? Well, let's do a few more, and let's see what we could do with this. Log base 7 of the 4th root, the quartic root of 7. I would probably change this to say log base 7 to the 1/4. And then this quarter, let's kick in front. And you could say 1/4 of log base 7 of 7. So we're just left with 1/4 times 1, which is just 1/4. So if you're starting to feel pretty good about these, I would say pause the video and try part B and part C on your own right now. Part B, there's a bunch of different ways we could do this. I would actually probably kick the 6 in front, kick the 2 in front. And if you had something like 6 log base 5 of 5 minus 2 log base 5 of 5, those reduce to 1s. You get 6 subtract 2, which is just going to give you 4. Again, there's actually multiple ways you could do that, but that's the way that I'll show you. And then for part C here, you could say log 1/4 of 16 squared, yuck, subtract log 1/4 2 to the negative 3. And I bet there's probably some ways we could clean this up a little bit better. Let's see what would happen. Let's see what we could do with this. This 2 we could kick in front here. And then you have 1/4 of 16 subtract negative 3 log base 1/4 of 2. Okay, so you want to simplify log a base of 1/4 of 16, and you could put that into exponential form, and then you could figure out what that would be, and you would get that's negative 2, because 1/4 to the power of negative 2 would be positive 16. If you wanted to, you could always say 1/4 to the power of what equals 16. 4 to the negative x equals 4 squared. X would have to be negative 2. So here we get 2 to the times negative 2, and we're going to subtract a negative, so we're going to add log. Well, what would you say this? What would be log 1/4, log with a base of 1/4 of 2? And if you think about that, you could rework that, and you would get negative 1/2. And again, if you're not sure of that, actually, I probably did that a little quickly here, plus 3 of negative 0.5. Okay, then you can always just set it up in exponential form. So you would get negative 4, and then this is going to be plus 1.5. And then that's going to equal negative 2.5. That's definitely a pretty hard question. I got to think that I probably could do this an easier way by changing things to 2's earlier on. I don't know. I would want to relook at that and see if there's maybe some other things that you could do for that. But that's I guess that's the way that I saw it for that question. Okay, well, let's take a look at example 5. And let's see what we could do with this guy here. So it says expand each log expression. Log base 3 of 3 plus log base 3 of x to the 4 plus log base 3 of y squared. Every time you have an exponent, kick it in front. And if you have something that you can simplify just as an easy answer, do that. That's the number 1. 1 plus 4 log base 3 of x plus 2 log base 3 of y. So hopefully that seemed reasonable. Okay, and then let's look at part B here. So you could say log, and this is going to be I'm going to rewrite this, and I'm going to say log 2x minus 5 to the power of a half subtract log 3. And then based off of that, I'm going to kick the half in front, and you could say 1/2 log 2x minus 5 minus log 3. That's as simplified as we can get for that. And then for part C here, log A subtract log B subtract log C. Okay. Definitely some pretty crazy questions there. Okay, let's go on to example 6. But before we go on to example 6, something was bugging me about part C from our previous example, and I'm sure I probably had 4 of you guys already ask me this question right here. I was thinking like this, something doesn't seem right. This is -4. This is -1.5. 4 subtract -1.5 is -5.5. Sorry about that. Yeah, that was bugging me. All right, let's go on to example 6. We got this is our final example, and we'll just go over a couple of rules here. So it says condense each log expression. So this is going backwards now. They're in some sort of expansion. You want to see what you can do to simplify it. So you could say something like log x to the 1/3. Kick this up top, undo the soccer kick rule, plus log x minus 1 to the power of 2. I would accept this, leaving that as a third, but probably it's a little bit more common to write it as the cubic root of x. And then what I would do is, if these are 2 logs with the same base, they're both base 10s, then you could add these, and they're being added together, then you could write it as a single log, where you could write something like that, and then now you have it all put together as one log expression. So take a look at that. Hopefully that seems like that would be something that you can do. Undo the soccer kick, put the 2 up top here for part B. Log base 3 of x plus 4 is squared, and it's being divided by x. Okay, part C. This 3 can go up top here. Log, and then let's see what we have here. We have a 5. Oh, that 2 can go up top here. And so you would say something like this: 5x squared over x squared plus 5 cubed. Make sure the bracket goes over the whole part of that, and that seems good. And then for part D, this is not saying y plus 1 in a bracket like that. And so what you want to do is, you have a log base 2. You've kicked the 3 up top here. And you have something here where you have just the number 1. And so let's change that number 1 to say log base 2 of 2. And then that way they all have a common log base 2. Okay, that's actually a really important point right there. Because then what you could say is you have log base 2 of, well, what do we have? We would have x, y cubed, and a 2. So let's go 2x, y cubed. So that's taking this guy, and this guy. Okay, that was a lot of details, and that's definitely a lot of info to take in for some of these questions. So just quickly, 2 additional rules to take a look at. We've looked at this from our 5.1 lessons. So this guy right here is allowed to kick in front using the soccer kick rule. And if you do that, then the log base b of b would reduce to 1. So that's just n. You might remember this rule from some previous questions. If you had something like 7 log base 7 of 10, the answer would just be 10. And that's when these two are the same. So if these b's are the same, then your answer is just n. Okay, good luck taking a look at these questions, and ask me lots of questions in class. Thanks. Bye.